Okay, so I just started the recording, which means everybody has to turn on their camera and audio again if they want to speak. I'm very happy to now continue with the focus topic. Today we have Andreas join us from Vito. He's working as a researcher there in the area of remote sensing, and today he's going to talk about their work related to CORSA and Terrascope, and I'm really looking forward to the insights we're going to get. With that, I'd hand over to you.
Yes, thanks for the introduction and for inviting me to speak. I hope you can see my screen at this point.
Yes.
Okay, perfect. Yes, so I'm Andreas from Vito Remote Sensing, which is the Flemish Institute for Technological Research. And yeah, I'd like to talk about Terrascope and CORSA for the next 15 to 20 minutes. If these two words don't mean anything to you yet, I don't think that's a problem, because I'll explain what's going to happen. So first, I'll talk a bit about Terrascope. It's a platform and what it is and why it's useful. Next, I'll talk about the CORSA model, which is something my colleagues and I have been developing at Vito, which is a compression model and more. And finally, we'll try to bring the two together and see what we can do with CORSA on the Terrascope platform. So what is Terrascope? Yeah, it's the Belgian collaborative ground segment for Sentinel missions, which is a mouthful. But it's basically a platform with a lot of different functionalities. First, and maybe one of the most important things, it's giving you very easy access to lots of satellite products. The satellite data, it's the archive for Sentinel missions. But there's also different products and related data sets associated to the original satellite sources. There's services. I'll give an example later on. But also very interesting is that there's cloud processing capacity. So you can really work with the data at the source. And only later on, when you need to download something, you only download the final product. You don't need to be downloading tons of intermediate data. And there's even a Neo Plaza, some kind of marketplace where you can exchange services or provide them for other users. And it's open for everyone. So everybody's free to open an account there. Different stakeholders or researchers. It's for everyone. And if you open an account, you get some free credits you can explore. Yeah, and just to mention, it's all funded by the Belgian Science Policy Office. So what type of data can you expect to find there? As I said, it's the archive for a lot of Sentinel missions at different atmospherical levels. It's very easy to download them or to process them in different ways, such as you want. It's also the archive for the PROBA-V missions and the spot vegetation. Other data sources, yeah, and it goes way back in time as well. There's really plenty to do with. Other data products you can find there, also the world cover maps, which, as the name suggests, give an indication of land cover types at a resolution of 10 meters. It's also been updated a few years in a row, and I think in the future also more updates will come. Or the Copernicus DEM is also there at different resolutions. And finally, there's data sources that are derived from the original satellite products, like air quality, water quality indicators, vegetation indices, the likes. Just to say, there's plenty of data there that you can immediately work with. But it's not just about the data. The platform is more encompassing. There's also services there. Maybe for now, I'll just give a brief example of one service that you can find there, which is CROPSAR, which is actually also a deep learning model that's been implemented on the back end of Terrascope, which takes in time series of Sentinel-1 and Sentinel-2 images, and it tries to fill the cloudy gaps in the Sentinel-2 images. So you have smooth filled in time series that you can use, for example, crop mapping or crop monitoring. So this is implemented there. If you make an account on the Terrascope, you can also use this service if you have need of it. So that makes it also interesting that you have access to these types of services. Then there is the processing part, where you can actually have a virtual machine that's linked to the data I mentioned before, or if you prefer, there's Jupyter notebooks. So you can really work with the data, explore it, do different type of processes. For that, there's the OpenEO API, which is a library that allows you to interact with the data, do all kinds of processing on the backend, so on the service of Terrascope itself, so that only afterwards you download the product that you're actually interested in after doing all the processes that you wanted to do. And at this moment in time, there's also been a lot of use cases implemented on top of this ecosystem. Again, I'll maybe just give one example, which is Terraflot, which is a use case by Vito and also UGent, where they built a workflow to monitor flooding events in real time and get other flood-related products. So this was built on top of the data and all the processing capabilities that are Terrascope. Now I'll go over to CORSA. Later on, I'll bring the two together. It might seem like a small jump, but it will come back. CORSA is a deep learning model for compression and analysis that we have been developing at Vito. Initially, it was developed with the idea of compressing images on board. So really do the compression at the satellite where it matters most, because I think most of us are aware, data volumes are ever increasing. There's more and more satellites in orbit producing data. This data needs to be stored. And especially for hyperspectral satellites, there was already this bottleneck of how do you actually downlink these huge amounts of data. So the model was developed to compress images on board, downlink only the compressed format, and then on Earth itself, you can either reconstruct the original image, or because it's a deep learning model, the compressed format, the representation is itself already very meaningful, and you don't need to reconstruct it to use it in downstream applications. You can immediately build on top of that. So CORSA tries to strike this balance between compression at one side. So you really save on transferring costs for data, especially if you're talking about these big volumes, and also on storing these data, because the compression goes up to, depends on the type of data, but I'll say more on this in a second. And on the other hand, the representation, so it's a deep learning model, and the compressed features are actually very useful in a sense of a foundation model that you can train directly downstream tasks, downstream specific heads on top of them, and in that sense, you save on labeling costs because you don't need that much data anymore, and the models converge faster. But orthogonal to this, there's also the edge implementation of CORSA, because we really want it to work as well on the side that it matters most, which is usually the hardware side. On the satellite itself, you would like to compress the data there to get maximum benefits. So we've really also been looking at optimizing hardware implementations. So the compression model can run on a satellite, on a drone, or on different types of hardware. Next slide gives an overview of the architecture. So it's based on the vector quantized variational autoencoder. It starts left bottom side, we start. So the original image that's captured by whatever, or that's stored on some server, can be processed by the backbone. In our case, it's usually a convolutional backbone, which is then giving you features at different levels. we usually work with 2 levels. So one that it says half resolution, we call the level 0, and one that's even further downscaled to a quarter resolution, which is the level 1. And then the power of the quantization comes in that the model is trained with a codebook that does the quantization part. So the codebook is a finite set of allowed vectors, and it forces the original latent representation, which is continuous, it's just continuous vector, to be, it forces that continuous vector to be one of the possibilities allowed by the codebook. Here at the 2 levels, we have a codebook of 265 entries, so 2 to the power 8, which means we can encode a single latent vector with 8 bits only. Because when we force, at the quantization stage, we force the latent representation to be discrete, allowing it to be only one of these possibilities. And that means we don't need to store the full vector. We only need to store the reference to the vector, which is an integer between 0 and 255. That's where you get big compression gains. Depends a bit on what type of data, as I mentioned before. For RGB near type of images, we usually have like a compression ratio of 20 if you don't want to lose any quality. But the more bands you have, the more there's correlations, the more you can usually increase this compression ratio. So for Sentinel-2, it's usually around 37, 38. And for hyperspectral data, where you really have hundreds of bands, you can even go to a factor 150 or more. And then on the decoder side, you can, so yeah, you store the indices as that's compressed representation. To decompress it, you go fetch again the full vectors. And these full vectors you can either feed to the decoder to reconstruct the original image, or just immediately use them in a different application. Now, as I mentioned, CORSA is some kind of, you could see it as some kind of foundational model, even though it's much smaller, also in parameter count. And it differs because it's not some kind of masked reconstruction that we do. We do a normal reconstruction task, since of course we want to have near lossless compression and reconstruction. So we're not interested in this masking part. But an interesting thing is that we've also found that the bottleneck, where you force the representation to be discrete, is in itself actually a very useful pre-trained task that really boosts the representations and the performance of downstream tasks. So we have tested this on a set of different downstream tasks at this point, among which are the Pickard net classification, parcel delineation, change detection, and land cover classification. At some point, I think we'd also really like to test this on broader benchmarks like GeoBench or Pangea that are coming out to see how it compares with other models that are very much specific trained for this. So that was the CORSA side, and now I'll try to bring the two together, so CORSA and Terrascope, because we've been implementing a demo on there, which is a Sentinel-2 based demo, where you can get embeddings, CORSA embeddings, and so integrate the CORSA embeddings in the Terrascope framework. For this, we have started with a subset of the major TOM dataset, which is a very expensive dataset for Sentinel-2. But at some point, we'd really like to just compress every image on Terrascope that comes in and store these embeddings there. But for this demo, we have limited ourselves to the Antwerp region, which is in Flanders, Belgium. And you can see that for this region, the original size of the Sentinel-2 images, 12 bands, was around 400 megabytes. But the CORSA features are only 10 megabytes. And so the download time is also correspondingly much, much slower. When reconstructing, you need to use the model, the decoder. So you lose a little bit of time on that. But it's a very lightweight decoder as well. And even on CPU, this goes very fast. And yeah, in a lot of cases, you don't even need to reconstruct it because you will immediately use the compressed representation in a downstream task. But so by using these compressed features, you get download times that are 10 times faster. But maybe even more important, you can store these data at much, much lower rates. And you have ready-use feature vectors that you can use in any task without needing to retrain a model. It's the embeddings that everybody's so fond of. So when I'm talking about compression and reconstruction, it's always nice to have some visual proof that it's working. So on the left side, you have the original Sentinel-2 RGB, and on the right, the reconstructed one. Here is the same for NDVI, so based on the original and reconstructed. And of course, it's also fun to visualize these embeddings in a way that brings out what they represent. So if you remember the architecture, there's two levels. So here is also visualization at the level 0 and the level 1, which is at half resolution and a quarter resolution. And then finally, there's one neat trick for CORSA. So we have the code book that in this case was 265 entries, so 265 possible vectors that are allowed in the latent space for a given level. But we have structured this latent, this codebook on a cube. So we have given it a 3D structure so that every index also has 3 components. And we can use these 3 components to colorize as well every vector in the latent space. And in this way, nearby vectors will have similar colors. And this allows you to also make a visualization of the compressed format itself. So you don't need to decompress to have this insight already, this extra information about the image, which could be really useful in the future when you want to do similarity search or retrieve features about the image when it's still in its compressed format. So without needing to decompress the entire image, you can already learn a lot about it. This brings me to the end, but just to tie it all together. So we have now these features stored on Terrascope that you can download very fast and reconstruct near losslessly. But you can also just use these features for fast prototyping and develop some kind of land cover model or do a flood detection or whatever you like. So that's it. You can try it out, of course. There's a link to the Terrascope platform, but also we have made a notebook that guides you through the process that you can try it out yourself, download some features, see what you can do with them. So that's it. I'm also here. I also like to thank my team. Some of them are here. And if there's any more questions, I'm more than happy to hear it.
Great. Thank you so much for the great presentation. Really insightful.
Thanks.
Maybe I can just start with a question. You mentioned near lossless compression, and we could also see in the visual examples that by the human eye, we couldn't really see any error in there. But I'm still wondering if you guys like quantified that in any metric, or if you tried out different compression settings to kind of find that good trade-off of now it's near lossless and a level we're ready to accept.
Yeah, I think the level of quality you want to have can depend on the use case. For us, we just strive to have the best possible reconstruction with the highest compression rate. We always monitor, like mainly we look at the signal to noise ratio. Yeah, and we strive to be around 50. It doesn't say much, maybe. But yeah, of course, this is something we try to keep good track on, that this remains high enough to be useful.
Okay, I see. And then maybe second question from my side. You also mentioned the CNN backbone, especially when you move towards like multispectral and hyperspectral data. Do you keep like the standard CNN architecture, or do you also do some sort of like spectral feature extraction?
So it's some kind of, yeah, the backbone with convolutional layers. We have, it's mainly composed of residual layers, but also pyramid sections. But so all the spectral, there's no specific pre-processing of the data before it's being fed to the model. It's really, the correlations are learned through the layers. And so the more layers you have in hyperspectral, the more you can get this compression because there's a lot of redundant data.
Okay, I see. Thanks. With that, I would open it up for more questions from the other people on the call. Yes, Christian, go ahead.
Oh, can you hear me?
Yes.
Perfect. Hey, I'm Christian. Andreas, we know each other, but maybe for the other
Yes.
guys. I'm Christian. I work as a data scientist at EuroTech, and we also are currently looking a bit into compression. So, Andreas, great talk. Thanks for the presentation. I think my question is a bit going in a similar direction as Isabel's question in terms of the reconstruction performance, because when we think about onboard compression, we need to kind of balance a bit, or at least like even bringing this concept of lossy compression, even if it's near lossless, into the room, like triggers a bit of a warning for some. So it would be super interesting for us if you do these kind of studies and you report on the reconstruction performance in a metric like RMSE. So for example, if you look at the Sentinel-2 L1C top of atmosphere, I think usually this is kind of a reflectance measurement that you get. You could look up the validation report by the MPC of those data sets and then compare the RMSE to the quality of the scientific measurement to give a bit of a feeling of how well the product is still aligned with the original kind of performance of the calibration. And so if you go towards use cases where maybe you don't only want to do segmentation, but maybe people want to derive some form of physical quantity from that measurement, it could be super relevant for them to kind of have that comparison. So I was also a bit interested in if you have any values in terms of PSNR or RMSE on the reconstruction performance.
Yes, so for sure we have done these experiments. I don't know the numbers by heart, but Bart is also in the call. We did at some point compare it with like the standard compression scheme. Bart, I don't know if you can mention a bit on what results we got from that.
Yeah, I don't know the results by heart, but we compared it to the CCSDE standard for hyperspectral compression and some JPEG 2000 for RGB-NIR compression. I don't know by heart what the numbers are, but we looked at peak signal to noise ratios, spectral angle mapper also for hyperspectral, and structural similarity indices, SSIM. But we'll have to get back to you with the specific numbers that we mentioned in some of the papers that we put out. I don't know by heart.
Okay. Yeah, but thanks anyway. I think the compression rates, they seem to be really nice. So, and I mean, visually also, it seems to be holding up quite well.
Yeah, there's one thing that's maybe also important to mention is that so we have the numbers on peak signal to noise ratios, but then it would be also beneficial if we could provide like a lower bound minimum reconstruction or maximum reconstruction error. At this point, that's not guaranteed for every image, so that's also something we want to explore further in the future, to have this minimum accuracy guarantee.
Yes, indeed. With the VQ-VAE architecture, you can fix the compression rate, but you cannot fix a lower bound on reconstruction error. So that's indeed something that a lot of people would like to have to get more confidence in the results. Indeed.
Cool. Thanks.
Yes, go ahead, Jonas.
Thank you very much for your talk. I enjoyed it a lot. I found it especially nice that you mentioned the OpenEO in the beginning. So I was wondering if there's already the connection made to access those embeddings through OpenEO already, given that Vito is heavily involved in developing OpenEO, or if that is a plan for the future or not.
Yes, so that's definitely the plan. For now, it's just this demo set, but we are in the process of making it much more extensive. And I think it will be for the near future that we can have these compressed version available for much larger coverage.
All right, thank you.
One more question from my side, as more of an outlook in the future. How do you guys see like the future of people accessing embeddings? Do you think it will, for Terrascope, also rather move towards having that one embedding product that is very advanced and strikes a good balance across different use cases and compression ratio? Or is it rather going to be different embedding products that maybe complement each other?
On that, I'm not entirely sure myself. I think a lot will depend on, if people find the good use cases with them, find they can be used. If the value becomes very clear, more and more products will pop up, and for sure also in Terrascope, more will be included. But I feel at some point it's still waiting a bit to see how will they be used and what exactly do people need.
Yeah, totally. Did you already get some feedback from your demo or see people playing around with those demo data sets?
Yeah, people have been playing around, but it's still not always clear what exactly they want.
Okay, I see. Okay. Any more questions for Andreas and the whole team? Okay. If that's not the case, I'm sure they're also happy to answer questions later on if you guys reach out.
Yes, definitely.
Great. But then for now, big thank you again. It was really great to have you share insights on that and very interesting.
Thanks for having me.
And this already brings us to the end for today. Last round of any more questions or anybody that wants to share something. If not, I would go on and close the call for today. Okay. Great. Then that's it for today. Thank you guys all for joining. Next call is in 4 weeks. Feel free to also invite other people that might be interested in these topics. And looking forward to seeing you soon then.
Okay.
Bye.
Bye everyone.
Thank you.
Thanks so
Bye-bye.
much. Bye-bye.
Bye-bye.
Thanks for hosting.
Bye.
Weekend.